Okay, so let's start now. Today is the 27th of June, Saturday. It's 11 a.m. and 2 minutes past. Today is the General Electronics class, paper 7. It's a follow-up class. Obviously, I have assigned the lectures, video lectures on the YouTube to you, and we'll be discussing. Rather, I do have take the review of those, and then we discuss the issues related to that. Before I start, I would like to ask that can everybody hear me clearly? सबको मेरी आवाज़ साफ सुनाई दे रही है? कोई नॉइस तो नहीं है, कोई इशू तो नहीं है? चैट में काइंडली लिखें यस और नो. ओके, बैकग्राउंड नॉइस तो नहीं है क्योंकि आज गर्मी ज़्यादा, तो मैंने ऊपर सीलिंग फ़ैन ऑन किया हुआ है. नॉर्मली मेरे पास छोटा पेडेस्टल फैन है तो वो रखा होता है ताकि उसकी नॉइज़ कम होती है. सो आई डोंट वांट एनी नॉइज़, सो इंटरप्शन ना हो आपको मेरी आवाज़ में. ओके, अगर क्लियर तो ठीक है, इट्स ओके, थैंक यू. ओके, सो today's topic is the we did last time the topic was field effect transistor. Before start the next topic, I would like to share. We don't have last time the time, and the last topic review. मैं आपको एक वीडियो शेयर करता हूँ. There is a beautiful video. Actually, I tried to embed that video in my video lecture, but due to the copyright, I think the YouTube didn't allow, so I removed that video. So I'm sharing this video with you. You can see that this is the animation rather of that complete process of the field effect transistor. There are two types, main types. One is the junction field effect transistor, and the other it's advanced. You can say the family or the version is the MOSFET. We will be discussing today later on. But this is the junction field effect transistor. So let me start this video, and you can see. Let me explain it. This is the field effect transistor. You can see this is typical. This is the channel, and this is these are the two gates. So P, this is the P, and blue is, these are the legends. Blue is the N channel. Okay. The voltage which is applied here, VDS. The terminals of the FET field effect transistors are called as drain. This is the collector in case of the BJT bipolar junction transistor. As you can see, the charge flow only due to the one type of the charges, which is the electrons or holes. So that's why it says not the bipolar junction. In bipolar, we have electron and hole both migration or the transportation of the charges, due to which the whole energy is carried inside the material. So here we have the what the we have explained in the previous class, that we have an N channel big semiconductor material. We dope two P-type materials, which is in this case is the pink one is the P-type. On the opposite sides of the, this is, if this is a bar, or it would be a rectangular bar. So these two, both P-type material are connected to the ohmic contacts like wires, copper wires together, and this common terminal is taken out, which is called the gate. The other two terminals on the opposite side of the N channel, one is called the drain, which is a collector in case of the BJT or bipolar junction transistor, and the other the second, this is one is the drain, the other one is a source or the emitter, like in the common. This is the common source configuration. We should have ground over here, but anyway. So the voltage applied between the drain to source is VDS. As we can see. Let me allow the, who is this?. So the what we have is we got video. So here we have the voltage applied between the drain and the source. You can see there is nothing, no obstruction in the path of the we can see in this case this is n-type channel. The majority charge carriers are the electrons. They are flowing through from the source to drain. So the if we apply the voltage P on this side and then and on this side, then what will happen? The current will start flowing. At the moment, it is zero because we don't have applied any VDS. Where the voltage is increased, the current will be increased. So the current will be flowing from positive to negative without any obstruction. There is no obstruction at all. So, and there is a gate here is kept at a certain voltage, plus minus. We can increase either minus voltage or the plus voltage, whatever. But normally in the gate voltage is kept at the reverse bias. This is the volt ampere characteristics curve. You can see the VDS and ID, this voltage and the drain current. You will see that how this is the gate voltage. Gate voltages for 0 volt, you can see the drain current is maximum. So let me start now. You can see it is self explanatory, or it can be demonstration is shown in the video. So I started the video now. This in this case, you can see that once the explained that this is the gate to source voltage, this is drain to source voltage, and once we have the increase the voltage 2 volt, the drain current start flowing. In this case, is electronic current is being taken. Electrons are moving from the negative to positive, but the conventional current is there with positive and negatives. Okay, so there should not be any confusion. There's a bit because the positive voltage is applied here, and still the gate is grounded from here. You can see because यहाँ इसके through लगा हुआ, so little bit. Still there is a channel, pretty big channel, where the freely electrons are flowing. Depending upon as it keep on increasing, you can see here for 10 volt, the gate voltage, the voltage is maximum. Now it is the, you can see that 0 volt is made VDS and negative voltage applied 0.5. Now you will see the current will reduce to 3 point, rather it, in this case it is increasing will be increasing 3.5 as we increase the VDS. The current is increasing along with, you can see the graph is also showing 5.1 milliampere. I keep watching this gate voltage. When it will increase, then the decrease will take place. So the description is also given here in see that. So now this is decrease again and then increase. Now you see -1 volt. Once it is increased -1 volt, we can see that the path is being squeezed between these two p-type gates, and that squeezing is causing the reduction in the drain current. Now this is the region, it's called pinched off region. As the voltage is, the gate voltage increase such that it is the -2 volt, which is the maximum voltage, then no current will be flowing. Although 10 volt is applied, the two depletion regions, here we call the reverse bias region, that takes place. Okay, let me take that again, explain it. This one, last one. So these depletion regions stretches, and they almost touch each other and block the flow of the charges flowing from the source to drain or drain to source. Conventional drain to source and electronic current configuration is a source to drain. So that's how the field effect transistor works. That was the video I wanted to share. I can share you with the email. I'll send it. You can find it on the screen, cast-o.matic.com. That is there, okay, on the website. You can see the link is given, screen cast-o-matic.com. Okay, now let's come to the today's topic, which is the, since it is a follow-up, I hope you have gone through, seen the read about it, but let's see. And also I have explained it in my video lectures. So this is the ELEC electronic special devices, SPD means special devices dash S1B. As the S1 we have field effect, and this is S1B. Uh, MOSFET, this is the MOSFET. This is also the type of the field effect transistor. MOSFET stands for metal oxide semiconductor field effect transistor. Again, also I have explained that these are the tutorials available on the internet. Let me take you the link. This is the link, www.electronics-tutorials.ws. On this link, you can find all these tutorials very beautifully uh, given those tutorials. So the next breed or the class of the field effect transistor is the MOSFET. Okay, ICs are also made integrated circuits later on from the either TTL IC or the MOSFET ICs, which are made from the MOSFET metal oxide semiconductor field effect transistor. Okay, let me explain this. The, as its name indicates, the construction of that this device, the here we have how this metal oxide semiconductor transistor field effect transistor is constructed. In this case, what uh, we have the N type materials. There are again for the two classes we will discuss that uh, the depletion and enhancement type, but at the moment you just see that there is a one N channel bar N type material. Two metallic contacts are taken out. Now this is the whole surface, and there is a bulk P type material on the opposite side, doped P type, which we call substrate. Okay, substrate is a surface upon which you mount another material or another arrangement. So that means the, what is a substrate? A substrate is a solid substance or a medium to which another substance is applied and to which that second substance adheres. Adheres means the stick together or place or mounted. So we had a ohmic contact here with a substrate as well. Excuse me. So what we have, these two N-type materials are there. P-type substrate is there. Then what we have two contacts from the N-type. And upon the surface of this whole the material, there is a silicon oxide insulator, SiO2. Okay, silicon oxide insulator. There was some mistake here, I have corrected that one. So then this is normally mica or the some insulating material can also be used, but in this case is silicon oxide. Then upon the silicon oxide layer, this is in micron, remember, it is very thin layer of this as a dielectric, you can call it, or the insulator. And then upon this layer, there is a metal electrode from the aluminum or some metal material, normally it is aluminum, is mounted. So altogether, what it forms, metal oxide field effect transistor. That's why it is called metal oxide. There is a silicon oxide insulator layer, and right above that, there is a metal sheet, thin sheet again. So it will act like the capacitor. Okay, it will act like a capacitor. We will see in a moment. The gate is there, Now the gate is present, we take a ohmic contact over here. So we have got now three terminals: the source, the drain, the gate, and the fourth terminal is substrate, which is kept at the negative potential with the source, connected with the source. Now this is the obviously depletion region, but what happens that actually this metal oxide semiconductor transistor is working in this case, particular case, when this plate is applied a positive potential, what will happen? This plate is, we have applied VDS obviously. So in the absence of the voltage, we don't apply any voltage. What will happen? So we see that their N channel, they will be uh, making, here we don't have the link between this. The material is being provided, but the N channel will be later on, I will explain in another slide in a moment, that will be when we put here apply the positive potential, what will happen? It will make this plate positively charged, and on the other side the negative charges will be populated, because this is positive, this will act like a capacitor, just like a capacitor, because the negative charges will, so it will populate the channel, and the negative, before that there were free charges were not available, because of there is a, we can say that this hole is the p type of substrate material, the which will not have the negative charges, but as we apply the positive charges to the plate, negative charges will be induced over here. So they will be populated here. This is actually type we call enhanced channel MOSFET, E-MOSFET normally. So when we apply the VDS voltage, now the population of the charges which are induced due to this positive gate voltage will cause the current flow from one terminal. In this case, if we have the VDS is applied over here positive, and from this side to this side, or electronic current from this side to this side, electrons will be flowing from negative to positive. Okay, so that's how that MOSFET works. That's in the theory that is given, but let me share with you. Now there are two types, as this is the symbolic mutations. The within the MOSFET, we will see that this is enhancement type. As I told you, there are two types. I will discuss that in the construction as well. Enhancement type, and the other is the depletion type. This is the depletion type. Okay, so enhancement type. First, you note down the symbolic notations. The rest you can see that the construction is almost similar, but only this is the N channel and the P channel. We have this N, these are the two N, the in between there's a whole substrate with a P, and channel is enhanced. This E type means when the positive polarity is applied, negative charges are induced over here, populated, and the channel is enhanced with the with the negative electrons over here. The P types disappear, and only N type electrons are present, and the current flows. So this is the N channel, this is the P channel, this is the other way around. When we apply the negative voltage over here, in this case the voltage will be reversed, then the positive charges will appear over here. The channel is populated with the positive charges or the holes, and the current will flow as a drain to source voltage is applied. So this is the symbolic. You can see this is the plate, which is the gate, and these are the three terminals. Now you can see this is different than the field effect transistor. We have got a third terminal as well. In the field effect transistor, we have a single plate and the angle, drain, and the source terminals. But here we have, you can see here, small short separations between these two small tiny three plates over here. and so as in this symbol as well. So in this case, we have the N channel, means the arrow is pointed inward, and for in. Okay, so you have to remember that configuration, that while drawing the symbol, that which one is the N channel, which is the P channel. So just remember that the N channel means the arrow is inward pointed. Okay, but right, the rest is the P channel, outward pointed. P is outward. If one is the inward, the other one is the outward. The only two types are there, in this case N channel and P channel MOSFET. The other, the D channel depletion, I'm going to explain that depletion again, but this is the symbolic notations are that they are single plates. N channel is again inward, this is the N channel, and this is the P channel. Obviously the whole you can see in the column above is P channel, this is also a P channel. So here there we don't have the short plates, the single one plate, drain is taken out and the source we have got, and similar drain is taken out and source and the substrate. So substrate is common to source. Okay, so let me now take the both those enhancement type and the first one. Okay, sorry. Okay. Okay, here we have both types. First we take the enhancement, because we have done the enhancement first. This is the we have just we have done. So this is the same I have redrawn, or rather taken that figure. So in this case what we have, the same thing I have explained, that there is a silica oxide. So what we have, silica oxide, there is the aluminum, this is the metal, the metal oxide. There are N type, the whole region is filled with the P type, which we call this bulk or the substrate. And in the absence of this gate voltage, this hole will be pink. Okay, there will be disconnect between these two. They are not connected, the N channels, the N type, these two, although we have taken the metallic contacts outside. So in this case is the common source we have applied. So when I have just explained that when gate is made positive, in the absence of the gate voltage, obviously the drain current is zero. But once the gate is made positive, this will make the positive plate will be positively charged. Inside this mica or the silicon oxide will polarize. So polarization will cause the induction of the here. This inside, this will be negatively charged, this will be positively charged, and then we have on the other side. Remember, this is the equal number of charges both, but maybe I have copy and paste a little bit extra, one or two. So on the other side we have this positive layer, which is attached to the substrate or the mounted on the substrate, will induce negative charges over here. Now, which will cause the current, as a drain voltage is DS, drain to source voltage is applied, the current to flow inside the channel. So we say channel is populated or enhanced. Channel is enhanced with these charge carriers, which are the majority charge carriers, in this case the N channel. Okay, so the what we have, this is called, that's why it's called enhancement MOSFET, E MOSFET. Okay, so this is the that type. I have shown you the symbolic the figures are the drawings. Okay, now what we have, this is called depletion MOSFET or depletion. This is the opposite to that one. we have a complete channel over here. Okay, complete channels. In the absence of the gate voltage, the current freely moves. Can when we apply it, then the from drain to source, the current moves very easily. But when the gate voltage is applied, in this case now for the depletion MOSFET, what we have, we apply now negative voltage over here to the gate. It will make this plate negatively charged. Inside polarization will take place in the silicon oxide, and this time the what we have, the this negative charges, what will happen, will induce from this side positive charges. Okay, this negative sheet will induce the positive charges. This positive charges induction will cause the reduction in the size of the channel. In the absence, if we remove this negative charge from here, what will happen? This whole channel, this much length, okay, this whole channel is available for the flow from this line. Okay, but as we apply the negative to the gate, the the this negative will cause positive, and the positive negative, and this negative will cause a positive on this side, either here or here. It makes the same, no difference. It makes no difference. So these positive charges will narrow down the channel. So we call it depletes the channel. So depletion MOSFET. Okay, the channel, the charge carrier channel is depleted. Here the charge carrier channel is enhanced, populated. Okay, this is the population of the enhancement of the channel with the charge carriers. This is the depletion of the charge carriers, of the main charge carriers, which are the electron, and the in this case electron are also in this case. So initially there were no electrons at all. They were populated with the negative electron due to this activity of the gate positive polarity. While so we say the channel was enhanced with the negative charge carriers. But in this case, what we see, that with the negative voltage, gated voltage, cause the positive injection of the charges inside the channel, which reduces the charge carriers of the n channel, n type, inside the channel, and we call depletion MOSFET. Okay, so that is the basic difference between the depletion MOSFET and the enhancement MOSFET or E MOSFET. So that's the all about the field effect transistor. So you go through the rest, the details are given, basic everything is defined over here in this description. Now let's come to the volt ampere characteristics curve. Already we have seen that, but it's similar to the common emitter. This is the common source. As you can see, the gate voltage is applied. This is the gate voltage plus 0.5 volt to up to minus 2 volt. So you can have the current over here. This is for depletion mode N channel. So volt ampere characteristics curve are given. This is VGS is 0 over here. So that is the given as the negative voltage is causing the drain current to drop, and the positive voltage causes the drain current to increase. So these are the symbols. Obviously we have already drawn that. There will be, I think, one more graph will be there, and this is the enhancement type. The positive will cause to go the drain current up, 0 will cause to minimum voltage. This is the obviously the page, the cutoff point, and this is the symbol. Okay, the amplifier, you can use MOSFET amplifier. The only construction is included. So, but if you want, for your sake of interest, you can see the similar. This is the self bias. 4 resistors are there. The same way, the rest we apply the same rule of the amplification as we have applied in the other one. Okay, so that's the all about the MOSFETs. You read that out and hope that basic concept I have clarified. Okay, I will take the question at the end. So you note down whatever question if you have in your mind, then अपने साथ एक notebook और एक रखें pen और साथ लेते जाएं. Now let's move to the next topic, which is the uni junction transistor. This is the ELEC-SPD-S2 topic number I have assigned. As its name indicates that uni junction transistor means as the transportation of the charge carried due to the only one single junction. As in bipolar junction transistor, we have two junctions. In this case, we have got only one junction. So we have this is the symbolic notation for the unijunction transistor. You can see that we call the three terminals in this case as well. We call the two terminals of the main bar are called the bases, or the B1 and B2, and the third one, which is the either P type or N type, depending upon, this is N channel bar, so we can have a P channel bar as well. So uni-junction transistor consists of one single junction. Uh, the P type material is doped on the one side, which is closer to one of the base. This is the distinction, remember, between the field effect and the this. In field effect, we have on the opposite both sides, but we have only one single side, this side. The very heavily doped P type material is uh, fabricated on the surface of the N channel bar, which is closer to 1 and B2 and little far away from the P1. This P terminal is called the emitter in this case. So it is a double base, rather diode we call it. These are two bases, and the here we have the other terminal is called the emitter. So if you take an equivalent circuit in terms of the obviously between B2 to E, there is a resistance. We can divide this whole channel into two resistance. We call it RB1, resistance between the this point, that is the where the emitter is connected. So that can be treated as a single diode. Now with PN junction. Okay, this is N type, this is P type, so PN junction diode. This point RB1 is obviously higher than the RB2, and we will see that it is variable because of the biasing from this side. The emitter biasing will make it be variable. Either it will be conducting drastically or it will not be conducting. So base voltage between VBB is the voltage base bias voltage between the two bases applied B1 and B2. Eta VBB will come in a moment later, that it is a standoff, is intrinsic standoff ratio, I intrinsic standoff ratio. So ISO intrinsic standoff ratio. Okay, so this is the basic construction. We have got two bases, one complete big N channel bar, P type material, very heavily doped, is mounted or fused on the one of the base, which is B2, which is at a shorter distance, and then the B1. B1 is at a longer distance, and the uni junction is formed in this case. Okay, so that is the basic construction, and this is the N channel bar. So similarly, for the other, we will see that unijunction transistor is a three-terminal semiconductor device which exhibits negative resistance and switching characteristics for use as a relaxation oscillator in phase control. This is the application in phase control, and the relaxation oscillator means the obviously relaxation time. We say the time period. So we can change the time period with the relaxation oscillator in this case. So go through the description. I will just come to the main circuitry. We have discussed this circuit. The description is given again. There are the various version or the codes of those transistors are also given. Now, this is now the VRB1 voltage drop across the RB1 obviously will be equal to RB1 divided by RB1 plus RB2 into VBB. So the voltage drop, I hope that there is some figure. Yeah. So that is the unijunction relaxation oscillator. Let me go back to be define. This is the voltage between across the RB1. Here voltage drop is the VRB1. Okay, so the VRB1 will be equal to the resistance RB1 divided by the total resistance. The voltage divider formula you have done so many times in the lab as well, so you are familiar with it. So that what that voltage means. So here we have the here for unijunction transistor is the resistive ratio RB1 to RBB above is called the intrinsic standoff ratio. Okay, intrinsic standoff ratio. This was I was missing that there, and given by Greek letter eta. The typical standoff ratio eta range from 0.5 to 0.8 for most common UJT unijunction transistors. So if a small voltage which is less than the voltage developed across RB1, that is the eta VBB, is now applied, now the emitter input terminal diode PN junction is reverse bias, thus offering a very high impedance, and device does not conduct. So that what it is showing that. So if it is in reverse bias, then the resistance is pretty high. So if it is reverse bias, it is not conducting. So that means that the resistance is high and the transistor will not conduct. The reverse biasing will cause the emitter B1 junction in the reverse bias mode, or in reverse bias mode you know that the no current is flowing. So even if the base biasing is applied VBB, the transistor will not conduct. That's what it means over here. Okay, so now if a small positive volt input voltage which is less than the voltage developed across B1 now applied to the emitter input terminal diode P. Now if PN junction is reverse bias, they're suffering very high impedance, diode does not conduct, so it is switched off and zero current flows. However, when the emitter voltage is increased and becomes greater than VRB1 or eta VBB plus 0.7 volt, 0.7 volt is the obviously junction voltage, the barrier voltage, obviously is for the silicon, where the 0.7 volt equals to PN junction voltage drop, barrier voltage, then it becomes forward bias and the unijunction transistor begins to conduct. The result is that emitter current eta IE now flows from the emitter to base region, So what it means that, go back to the figure, yeah, here. So when it is forward bias, what happened that when the voltage is greater than this eta VBB, this is the obviously plus 0.7 volt of this one, this forward biasing voltage will cause the breakdown of this resistance in this particular region, and it will heavily conduct. So the transistor is called now fired on or switched on in this stage. Transistor will start conducting. VBB is already applied, so it will start conducting heavily. So here the main how the unijunction transistor works by putting changing the emitter voltage can set the transistor into various oscillatory modes from negative to positive or positive to negative. For negative, it will be reverse bias. For positive, it will be forward bias, and so on and so forth. That's why it's called relaxation oscillator as well. So that's the main functioning of the unijunction transistor. You can see that over here. This is the typical unijunction transistor relaxation oscillator. You can oscillatory pulses are being here. We will have the negative pulse. Here we will be having the positive pulse. Once this is a typical transistor unijunction transistor oscillator. This is the 0 volt. This is a VB1, VB2. So you can take the two type of pulse. This is the spikes. We can say the relaxation oscillator. We can have the quick voltage rise spike, and then we have relaxation discharge is taking place, and the positive pulses are being generated. So this is used for the triggering as well. The fast switching. If you want to trigger, you triggering means just like you trigger bullet from the gun. So you want to initiate a certain process in the electronic circuit, trigger the circuit with a certain pulse for a very short. A pulse fed into a circuit for a very short time. That's called triggering. Okay. So these are the typical pulses which are generated by the this UJT oscillator, relaxation oscillator. It's not in course, but you can see it as an example. It is also used for the phase control, controlling the phase by injecting these pulses. We can have the various applications. Okay, so this is the unijunction transistor UJT. Basic construction and the working mechanism is required in this case. Special device, how they work, how their mechanism, what is the construction, what is the symbolic notations, and inside working principle is in your course. So with this we reach to the end of this topic as well. Now the last topic is the third topic which I assigned is the now called the SCR, silicon control rectifier. You can see we are now getting more further. We have started from the diode where two p-n junction were fused together. First we rather discuss the construction of the p-n junction, p-type material and n-type material. Then they were of no use, p-type and n-type. Even we went from the intrinsic semiconductor to the extrinsic semiconductor, and then extrinsic semiconductor p-type and n-type material were of no use unless until we fuse them together to make the p-n junction diode. Then we extended further. That p-n junction diode was used as a rectifier or other applications. Further we extended the solid state devices to the new devices, that's a PNP transistor, which is a bipolar junction transistor. Now we further have, these are the special devices obviously. So this is silicon control rectifier, or popularly known as thyristor. Thyristor is the also the name of that. So you can see here what we have. It is 4-layered PNPN. Instead of 3 layers, 4-layer device thyristor. It has 3 terminals. One is called anode, and the other is called cathode. This is a unidirectional, bidirectional layer. I mean, we have to make positive over here, negative over here. we cannot apply negative over here and positive over here for the conduction. Obviously, the main purpose of all these devices is to control the flow of the current. So we have the gate on the one of the P type, the other side close to the N. So these are the four P and P, and material, semiconductor material are alternatively connected or fused together. But in fact, what we have, if you see this SCR, a silicon control rectifier, is made of two, inside there are two transistors fabricated in fact. One is the PNP, this is the transistor 1, the other was NPN. So if we have, we cut this, chop that into half here and half here, okay. If you just chop that, slice off the small part of the full part of P and the small half parts of the NP, these two, and here the half parts of NP and the full part of the N, slice them away, then in fact these are the two PNP and NPN transistors connected together, such that the emitter, the base of the transistor 1 is connected with the collector of the transistor 2. Okay, and similarly the collector of the transistor 1 is connected with the base of the transistor 2. So that is the main actually inside the construction of the PNPN silicon control rectifier. So what we call, one of the three terminals are there. One is the anode, which is a positive. We keep here positive polarity, whichever you want to apply from here, and the other one is the negative. Cathode is negative. Gate is now kept at the obviously you can see the biasing. Okay, this is the simple biasing of the, in the absence of the gate voltage, it or the reverse bias voltage, the gate, the transistor is in a turn off. This whole SCR is turn in the SCR is in a turn off position. The current will not flow through, the load current will not pass through. So this is used to control a certain load current of the high power devices. So we can trigger this, switch it on and switch it off by the gate voltage. The gate current, when it is applied, then it will be forward biased. Once it is forward biased, obviously the voltage applied across the anode to cathode, that will cause the current to flow through. So that whatever the load current applied over here, it will allow this current to pass through. We say it is fired on, SCR is fired on when the gate is made forward bias. So gate voltage, the gate current plus the anode current, that will constitute the total current IA plus IG towards the cathode. So the silicon control rectifier is just a thyristor, the more commonly known as the similar in the construction to the transistor. This is the symbolic notation for the thyristor. We have a diode and the gate, which is angle G. Diode was one positive side, anode, the other was the cathode, K. So details are further described in the topic. I hope you have read that, downloaded that one. So this is, let me see the application. The silicon control rectifier is one of the several power semiconductor devices. I mentioned as a power is used to control the power, turn on or turn off semiconductor devices, along with the triacs, that is a triode ACs. There is other type of triacs and diacs as well, and diode is diacs and triacs, two other types. I will upload those as well. At the moment I am just restricting to the SCR only. So that are capable of acting like a very fast solid state AC switch for controlling AC voltages and currents. So for the electronic students, this makes these very handy solid state devices for controlling AC motors and lamps. Lamps for the phase control. Now the thyristor is a three-terminal label anode, the three-terminal device labeled as anode, cathode, and gate, consisting of three p-n junction, which can be switched on. You can see here that we have three p-n junctions. Okay? Remember, it is mentioned four semiconductor materials layers, PN, but in between there are three junctions. It can be switched on and off extremely at a fast rate, or it can be switched on for the variable length of time during the half cycle, deliver a selected amount of the power to the load. The operation of the thyristor can best be explained by assuming it is made up of two transistors connected back to back as a pair of complementary, we call it this now. Connectivity of these transistors is also known as the complementary regenerative switches. They complement each other, obviously. So this we have already discussed. So this is the basic operation, just by triggering the gate voltage that makes the transistor to turn it on and off. Obviously the phase control is the main, obviously in this case, through phase controlling we can control the the AC large load currents flowing from one direction, unit direction only, in this case. So one thing more, this is the typical actual thyristor. ये अभी तक आपने देखी वो symbolic representation से, this is the, अगर कहीं shop में जाएं तो देखें, you are looking for the various other shapes are also available, but this is one of the, because it is very heavy load current के इस्तेमाल होता है, तो metallic बना हुआ है, उससे heat ताकि से evolve हो सके, heat can evolve. So that is the volt ampere characteristics curve. A little bit strange. You can see this is the current, load current, positive. This is the negative. This is the forward voltage. The gate is being forward biased. The gate is triggered. When the gate is triggered on, you can see the large current is flowing through, positive current. This is load current. And further, if it is increased, then we can have the knee voltage. We can see that the off state forward voltage blocking, but if the gate is triggering point, we can see this is increasing, but knee voltage, at a knee voltage the breakover voltage takes place. So but it will ultimately lead to the on state if the gate is turned on in the this SCR. So this is the conventional current which is flowing from positive to negative, and the gate is being triggered. In the reverse bias, we can have the reverse breakdown voltage may also take, negative current may also flow inside the this the device. So this is the volt ampere characteristics curve for the it is a typical, you can see the diode, but with the three characteristics curve. In this case we get, it is not a transistor, but it is a special device. Okay, rest is given within the theory. You can go through and read it out. Okay, so with this we reach to the end of the topics. Now I will take your questions. If you have in your mind, let me go back and see how many students are with me. Okay, there are 11 students. Okay, anybody have any question so far, whatever topic we have discussed? They can now write in the chat box, and we can discuss the question. Turn on your mic if anybody have any question. जी, किसी का कोई सवाल है, कोई क्वेश्चन है, प्लीज go ahead and ask. I hope everybody is listening to me. मेरी आवाज़ आपको आ रही है? My mic is showing, which is vibrating here. Okay. Uh, then anybody, any question? कोई क्वेश्चन हो तो आप पूछ सकते हैं प्लीज. Okay, general question, any question if you have in your mind. Anybody wants to talk? Oh, I can see the strength is very small still. 10, 11, 13 out of 34 class. So this is a little bit very discouraging. Okay. एग्जाम के बारे में बताएं तो बस इंशाल्लाह आई होप दैट यूनिवर्सिटीज विल बी ओपन इन सितंबर. यूनिवर्सिटीज खुल जाएंगी और बीएस के लिए तो हमारी एक मीटिंग हुई है, उसमें तो हमने डिस्कस किया है उनका, तो हम कंबाइंड एग्जाम हमने रिकमेंड किया है. If the universities are open, then your exam will be in the department, inshallah. Or you will be informed well in advance. लेकिन अगर यूनिवर्सिटी ना खुली, then that will be taken through online examination. ऑनलाइन एग्जामिनेशन आपका इस पे होगा, उसमें कुछ क्वेश्चन पेपर वगैरह सेट करेंगे, ओपन बुक एग्जाम होगा, आपको टॉपिक्स असाइन किए जाएंगे और टॉपिक्स एक कॉमन भी हो सकते हैं और उसमें सर्टन प्रॉब्लम्स जो है उसमें दी जा सकती हैं और वो प्रॉब्लम आपने सॉल्व करके प्रोवाइड करने होंगे ऑनलाइन एग्जाम की सूरत में. लेकिन चांसेस यही हैं कि 2 तारीख को मीटिंग हो रही है, यू ऑल नो. सो द गवर्नमेंट इज थिंकिंग टू ओपन द यूनिवर्सिटीज फर्स्ट और फेज वाइज करेंगे एकदम नहीं. ओके, वट एवर द प्लान वी विल शेयर विद यू एंड यू विल रादर यू नो बेटर देन अस. आपको पहले आपको इसकी सारे मालूमात हो जाती हैं. सो होपफुली आई होप दैट एग्जाम विल बी इन द एग्जामिनेशन हॉल्स हो जाएंगे इंशाल्लाह. सो पेशवा यूनिवर्सिटी तो एग्ज़ाम अनाउंस किया हुआ है सितंबर का. यू कैन गो टू द वेबसाइट एंड सी, पूरा शेड्यूल है, लेकिन प्लस माइनस में चेंजेस आ सकती हैं डिपेंडिंग अपॉन कोर्स वर्क. हमारा हमें ये दिए गए डेडलाइन बाय अगस्त, दी 1 अगस्त, यानी जुलाई के एंड तक हम ये ख़त्म करने हैं. जून एंड जुलाई, दीज 2 months फॉर द कंप्लीशन ऑफ रिमेनिंग कोर्सेज. और बाकी जो है एग्ज़ाम इंशाल्लाह उसके बाद आप जो यूनिवर्सिटी डिसाइड करेगी आपको इन्फॉर्म कर दिया जाएगा. एनीथिंग एल्स? Okay, good. The students say it's clear. Nice to see that whatever the small number has joined and they are following. So please, again, I request again and again that the share this online activity, means the whatever the video I have uploaded and the lecture notes I have uploaded with your those friends who are not attending. Okay, be in touch with them and inform them that go ahead and see those lectures, video lectures and the notes as well. Prepare yourself for the remaining courses. So that will, you should help your friends. Maybe some of the friends don't have the accessibility, so try to manage, and if you can provide them this soft form, if you can ask him to get this soft form and come and visit you if he or she is nearby residing, even if it is in the one village or the other village, then one day you can provide them, tell him or tell her that bring the USB and copy the data to that person. So you help that out. This is a very extraordinary situation. Nobody expected that, but we should help each other. Okay. Okay, then we will end over here, and inshallah we will meet again in the next meeting. Till then, goodbye. Let let me change attendance.